In 2013, a group of astronomers was combing through a map of the most violent explosions in the known universe, and they found something that should not have been there. These explosions are called gamma-ray bursts. Each one outshines entire galaxies for a few seconds. They are the brightest events the universe produces, and astronomers have been cataloguing them for decades. The plan was straightforward. Map where the bursts fall in the sky. Check whether they are evenly spread. Standard statistical work. The kind of analysis that usually returns a clean result and gets filed away. This one did not return a clean result. In a specific patch of sky, at a specific range of distances, the bursts were clustering, not randomly, not subtly. They were piling up in a region of space in a way that a smooth, evenly distributed universe simply should not produce. The team looked for an error. They checked the instruments. They looked for a bias in how the data had been collected. The clustering held. What they were looking at, if it was real, was a structure roughly 10 billion light-years across. 10 billion light-years. The entire observable universe is about 93 billion light-years wide. The thing they had found stretched across 1/10 of that. Everything humanity has ever seen, every galaxy we have ever mapped, every signal we have ever received from space, all of it fits inside a sphere, and this structure spans 1/10 of that sphere's diameter. Cosmology has rules about how large things are allowed to be. Those rules come from some of the most carefully tested theory in all of science. They predict a ceiling on structure size. That ceiling sits at roughly 1.2 billion light-years. Anything coherent, anything you could point to and call a single object, should be smaller than that. The structure these astronomers were looking at was not slightly above the ceiling. It was not twice the ceiling, not 5 times. It was more than 8 times the size that the standard model of cosmology says a structure can reach. It has no business being that large. That is not a casual observation. It is a direct challenge to the framework that modern cosmology is built on. The cosmological principle, the assumption that the universe is uniform on large enough scales, is not just a background belief. It is a load-bearing wall in the standard model. Pull it out, and a significant amount of what we think we understand about the universe has to be re-examined. The discovery triggered immediate debate. Some researchers accepted it. Others pushed back hard on the method. The argument has not been fully settled. And the stakes are real, because if the structure is genuine, the universe built something that the current rulebook explicitly says it cannot. That is where this begins. A map of the most violent explosions in existence, and somewhere in the data, something vast enough to rewrite the textbooks. And to understand why it matters, you first have to understand what 10 billion light-years actually is. The number 10 billion light-years does not mean anything to most people, and that is not a failure of imagination. It is just that nothing in ordinary human experience prepares you for what it points at. Start with the basic unit. A light-year is not a measure of time. It is a measure of distance. Specifically, it is the distance light travels in 1 year, moving at roughly 186,000 miles per second. In a single second, light crosses the distance between New York and Los Angeles about 62 times. In 1 year, traveling at that speed without stopping, light covers about 5.88 trillion miles. That is the unit, 1 light-year, nearly 6 trillion miles. Hold that number in your head because we are going to need it. The nearest star to our Sun is Proxima Centauri. It sits roughly 4.2 light-years away. That means the light arriving at your eyes from Proxima Centauri tonight left that star in the year 2021. If you wanted to send a message there at the speed of light and wait for a reply, that conversation would take more than 8 years to complete. No spacecraft humanity has ever built could reach it within a human lifetime. 4 light-years is by any practical measure unreachable. and 4 light-years is the smallest gap between stars in our neighborhood. Now scale up. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. It is shaped roughly like a flattened spiral disk with a dense bulge at the center. Across its widest point, it measures about 100,000 light-years. If you could somehow travel at the speed of light from one edge to the other without stopping, the journey would take 100,000 years. The civilization that launched you would be unrecognizable by the time you arrived, if it still existed at all. The Milky Way is enormous by every standard that matters to a human being, but we are just getting started. Beyond the Milky Way, the nearest large galaxy is Andromeda. It hangs about 2.5 million light-years away. The light reaching you from Andromeda tonight has been traveling since before the earliest stone tools were made on Earth. 2.5 million years in transit, crossing empty space, arriving now at your eye or at a telescope lens somewhere on this planet. Andromeda is close by cosmic standards. It is our nearest significant neighbor. The Milky Way and Andromeda are both members of a collection of galaxies called the Local Group. It contains more than 50 galaxies in total, including both large spirals and dozens of smaller dwarf galaxies. The Local Group spans roughly 10 million light-years from one edge to the other. 10 million light-years. That is 100 Milky Ways laid end to end. The whole thing, every galaxy we are gravitationally bound to, fits inside a bubble 10 million light-years across. The Local Group is itself just one small knot in a larger structure called the Virgo supercluster, which stretches about 110 million light-years across and contains dozens of galaxy groups and clusters. And the Virgo supercluster is just one lobe of an even larger supercluster called Lambda-CDM, which spans roughly 500 million light-years and contains the mass of 100 million billion suns. These are the structures that feel staggeringly large when you first encounter them. They are the things that make astronomers pause. But even Lambda-CDM is not close to the scale we are working toward. The observable universe, the entire sphere of space from which light has had time to reach us since the Big Bang, spans approximately 93 billion light-years in diameter. Not the whole universe, not all of space, just the portion we can see from here, the region bounded by the distance light could travel in 13.8 billion years through an expanding cosmos. 93 billion light-years, everything we have ever observed, every galaxy, every quasar, every faint smudge in the deepest telescope images, fits inside that sphere. Here is a scale model worth holding in your mind. If you shrink the observable universe down to the size of a regulation football field, the Milky Way becomes a grain of salt somewhere near the middle of it. Not a pebble, not a speck of dust. A grain of salt. The entire galaxy containing our Sun and 400 billion other stars. All the stars you can see on any clear night from anywhere on Earth, compressed to the size of something that falls off a pretzel. That is the relationship between our galaxy and the full scope of what we can observe. This perspective reveals something profoundly humbling about human existence. We inhabit one planet around one star, in one galaxy that occupies one grain of salt on a football field-sized model of the observable universe. The vastness is not merely large, it is systematically indifferent to our presence. Yet this grain of salt contains everything we have ever known, every human thought, every discovery, every moment of meaning or beauty we have experienced. The scale disparity is so extreme that it borders on absurdity, and yet we discovered it. Some arrangement of atoms on that grain of salt figured out how to measure and map structures so large they defy intuition. This contradiction, our smallness and our ability to comprehend smallness, sits at the heart of why the cosmic scale matters at all. Now introduce the structure. The thing the astronomers found in 2013 measures approximately 10 billion light-years along its longest dimension, 7.2 billion light-years wide. nearly 1 billion light-years thick. These are not the dimensions of a thin sheet or a narrow filament. This is a three-dimensional region of space with substantial depth in every direction. 94,000 Milky Way galaxies placed side by side would barely span the length of it. That is not a comparison that helps much, because 94,000 of anything is hard to picture. But try it another way. The distance from Proxima Centauri to our Sun, that 4 light-year gap we started with, is completely invisible at the scale of this structure. So is the Milky Way itself, so is the local group, so is Lanakeia. Every structure we described on the way up here, every step in the ladder from nearest star to nearest galaxy to nearest supercluster, disappears into the noise when you try to mark it on a map of the Hercules-Corona Borealis Great Wall. The structure does not contain multiples of our galaxy. It contains multiples of everything we have ever considered large. On that football field model, where the Milky Way was a grain of salt, the Hercules-Corona Borealis Great Wall would stretch across roughly 10 yards of the field, 1/10 of the entire length, not a faint smear near one end zone, a visible substantial portion of everything the model contains. That is the number, 1/10. The structure they found stretches across roughly 1/10 of everything we can observe from Earth, and it has no business being that large. To understand what the Hercules-Corona Borealis Great Wall actually is, you have to understand what kind of universe it lives in. The universe is not a smooth, uniform spread of matter. It never was. If you could pull back far enough to see the whole observable universe at once, what you would find is not a fog of evenly distributed galaxies. What you would find looks more like a sponge, or foam sitting in a bathtub. Enormous empty bubbles surrounded by thin walls and threads of matter. Dark voids so large that entire galaxy clusters would seem tiny against their interiors. And running through everything, connecting the dense patches to each other, a network of long filaments carrying the overwhelming majority of the matter in the universe. This is the cosmic web, and it is the fundamental architecture of everything at the largest scales. To understand how it got there, you have to go back almost 14 billion years. The universe just after the Big Bang was not perfectly smooth. Close, but not perfectly. Tiny quantum fluctuations in the density of the early universe meant that some regions had slightly more matter packed into them than others. Not dramatically more. The differences were extraordinarily small, but gravity does not care how small the difference is. Gravity is patient. Over millions of years, the slightly denser regions pulled in more matter from their surroundings. The slightly less dense regions gave matter away. That feedback loop ran for hundreds of millions of years, then billions of years, and the small differences compounded. Dense regions became denser. Empty regions became emptier. What started as a barely perceptible ripple across the fabric of the young universe grew into the web structure you see mapped in modern galaxy surveys. The nodes of that web are the places where the densest threads cross. Galaxy clusters form there. These are not single galaxies, but collections of hundreds or thousands of galaxies, all bound together by gravity, sitting in vast halos of dark matter, the hottest and most massive concentrations of normal matter in the universe. Between the nodes, the filaments stretch outward. These are long, relatively narrow highways of matter, sometimes hundreds of millions of light years from end to end. Galaxies form inside the filaments. Gas flows along them. They are not static structures but active channels, funneling matter toward the dense nodes where clusters sit. Between the filaments and walls there is almost nothing. These empty regions are called voids. A typical void might be a few 100 million light years across. Some are larger. Inside a void you might find a handful of galaxies spread so thinly across such enormous volume that the average density is a fraction of what you would measure inside a filament. If you were a hypothetical observer sitting in the middle of a cosmic void, the nearest galaxy cluster might be hundreds of millions of light years away in every direction. the night sky would look sparse in a way that is hard to imagine from our position inside a filament. The walls are somewhere between the filaments and the voids, flat, sheet-like arrangements of galaxies forming the surfaces of the large empty bubbles. When you look at a cross-section of a galaxy survey, these are the boundaries you see. The sponge analogy works because the voids are the holes and the walls and filaments are the material surrounding them. The foam analogy works too because the bubbles press against each other and their boundaries are the walls. Either way, the picture is the same, a connected network of structure separated by enormous emptiness. Now, here is something worth holding on to. Most of the ordinary matter in the universe, the atoms, the gas, the stars, the galaxies, lives inside the filaments and walls. The voids are genuinely empty by comparison. This means the cosmic web is not just a description of how galaxies are arranged, it is a description of where almost everything is. If you want to find a galaxy, look in a filament. If you want to find a galaxy cluster, look where the filaments cross. The voids contain almost nothing, and they make up most of the volume of the universe. Galaxy filaments come in a range of sizes. Some are relatively modest, connecting a few clusters across a few 100 million light-years. Others are larger, more substantial, part of what astronomers call superclusters. Our own Milky Way lives inside a supercluster called Laniakea, which stretches roughly 500 million light-years across and contains the mass of more than 100 million billion suns. That sounds enormous, and by any human measure it is. Laniakea is one of the largest named structures in our immediate cosmic neighborhood, but it is still a local feature of the web. Zoom out far enough, and Laniakea is just one node among many. This is the framework that makes the Hercules-Corona Borealis Great Wall legible. It is a filament, an extreme one, but the same kind of structure that shows up everywhere in the web, built by the same process, driven by the same physics. Gravity gathered matter into threads. Threads formed walls. Walls enclosed voids. The web emerged. What makes the Hercules-Corona Borealis Great Wall remarkable is not what it is, but how large it is, because the web was not supposed to keep growing at that scale. Standard cosmological models predict that the web reaches a natural ceiling. At large enough scales, the density fluctuations that seeded the structure in the first place were too small, and the time available for gravity to amplify them was too short. Above a certain size threshold, the web should look smooth. The large overdensities and underdensities that define the filaments and voids at smaller scales should average out. The universe at sufficiently large scales should look the same in every direction, roughly uniform, roughly featureless. The scale where this smoothing was expected to have taken hold is somewhere in the range of a few 100 million to perhaps 1 billion light-years. Above that, organized structure should not exist. The Hercules-Corona Borealis Great Wall sits somewhere in that web, but at a scale that the web was never supposed to reach. The tool that made this discovery possible is one of the strangest instruments in astronomy. Not a telescope exactly, not a detector pointed patiently at a single target. The instrument is the universe itself, scattered with the most violent explosions that physics allows, each one going off once and never again, each one briefly outshining everything around it by a factor that defies easy comparison. Gamma-ray bursts are the most energetic explosions in the known universe. When a massive star runs out of fuel, its core can collapse in under a second, triggering a catastrophic implosion that drives a jet of energy outward at nearly the speed of light. The result is a flash of gamma radiation, so intense that a single burst, lasting anywhere from a fraction of a second to several minutes, can briefly outshine the entire observable universe in high-energy light. Some are caused by collapsing stars. Others come from two neutron stars spiraling together over billions of years. and finally merging in a collision that releases more energy in milliseconds than our sun will produce across its entire 10 billion year life. Either way, the explosion is brief, ferocious, and unrepeatable. It happens once, and then it is gone. What makes this relevant to mapping cosmic structure is where these explosions happen. Gamma-ray bursts tied to collapsing massive stars occur in galaxies where new stars are actively forming. Massive stars burn fast. They live tens of millions of years at most. That means they die close to where they were born, inside the dense star-forming regions of their host galaxies, because star formation traces the distribution of matter across the universe. The locations of gamma-ray bursts serve as markers for where matter has concentrated. Plot them on a map of the sky, and you are, in a rough sense, plotting the skeleton of large-scale structure. The other thing that makes gamma-ray burst uniquely powerful as a tool is how far away they can be seen. An optical survey of galaxies runs into a hard limit. The farther away a galaxy is, the fainter it appears. Eventually, even the largest telescopes lose the signal. The deepest galaxy surveys reach out perhaps a few billion light years with reasonable completeness. Gamma-ray bursts punch through that limit because they are not steady faint objects, but sudden, violent flares. At their peak, the brightest of them can be detected from halfway across the observable universe. Some have been measured at redshifts above 9, meaning the light left them when the universe was less than 500 million years old. No galaxy survey comes close to that depth. If you want a tracer of structure that reaches back toward the earliest epochs of cosmic history, gamma-ray bursts are one of the very few options available. NASA recognized this potential and launched the SWIFT gamma-ray burst mission in 2004. SWIFT was designed to do something no previous satellite had managed reliably. When its burst alert telescope detected a gamma-ray burst, the satellite could pivot its more sensitive instruments toward the source within about a minute, catching the afterglow before it faded. That afterglow is the key. The initial flash of gamma radiation carries energy but not much spectral detail. The afterglow, glowing in X-ray optical, sometimes radiolight as the explosion shockwave plows into surrounding gas, contains identifiable spectral features. Specific emission and absorption lines from known elements appear shifted toward longer wavelengths depending on how far the light has traveled through an expanding universe. Measure that shift and you have the redshift. From the redshift, you can calculate the distance. This is how a three-dimensional map gets built. Each burst SWIFT detected, and whose afterglow was followed up by ground-based telescopes, gave astronomers a single point in space, a position on the sky combined with a distance derived from the redshift. Stack enough of these points, and you have a scatter plot of explosions distributed across billions of light years in 3 dimensions. The question you can then ask is whether those points are distributed randomly, as a smooth and featureless universe would predict, or whether they cluster, piling up in some regions and leaving others comparatively empty. This is exactly the question the team studying the Hercules-Corona Borealis Great Wall was asking. The depth of the SWIFT catalogue is what set this approach apart from earlier work. Previous gamma-ray burst missions had detected bursts but could not pivot fast enough to catch the afterglows reliably. That meant redshifts were hard to measure. Without redshifts, you have positions on the sky but no distances. A 2-dimensional map of the sky tells you almost nothing about 3-dimensional structure. SWIFT changed that. By the time the Hungarian and American team began their analysis, they had access to a catalogue of hundreds of bursts with measured redshifts, spread across a huge range of distances. That was enough to start looking for patterns. This observation demands your sustained attention. The most powerful of these explosions have been detected from distances so extreme that their light left the source more than 13 billion years ago. One burst recorded in 2009 was so far away that the universe had not yet finished its first billion years when the explosion occurred. The light crossed the entire subsequent history of the cosmos to reach a satellite in Earth orbit. You could argue that gamma-ray bursts are less instruments than time machines, each one delivering a message from a universe that no longer exists in the form it had when the message was sent. That is the power of the tool. But power comes with limitations, and the limitation here is significant. The Swift catalogue, and every catalogue built before or alongside it, was assembled under conditions that were never perfectly controlled. Different satellites with different detection thresholds covered the sky at different times, with different sensitivities to bursts at different energies. Ground-based follow-up observations required to measure the redshift from the afterglow depended on which telescopes happened to be available and pointing in the right direction when the burst occurred. Some bursts were followed up thoroughly, others were not. Some parts of the sky were watched more carefully than others. Some redshift ranges were sampled more densely than the data's apparent coverage implied. The result is a catalogue that is not a clean, uniform sampling of the universe. It is a patchwork, stitched together from dozens of observing campaigns with different characteristics and uneven coverage. The catch is that gamma-ray bursts are not perfectly uniform traces of the universe. That single limitation sits at the center of everything that came next. In late 2013, a team of Hungarian and American astronomers was doing something that sounds fairly routine, running a statistical check on the sky positions of gamma-ray bursts in a large data catalogue. István Horváth, John Hakkila, and Zsolt Bagaly had been working through data collected by NASA's SWIFT mission, cross-referencing it with redshift measurements pulled from ground-based telescopes around the world. The goal was straightforward. Were these explosions scattered evenly across the sky, or were they clustering? Routine work, the kind of analysis that usually produces a clean result and gets filed away. It did not produce a clean result. The team was sorting the bursts by redshift, grouping them by distance, and examining whether each distance slice showed a uniform sky distribution. Most of the slices looked normal. The explosions spread out roughly evenly, no suspicious concentrations, nothing that demanded attention. Then they reached the slice corresponding to a redshift of approximately 2. That is a distance so vast it corresponds to light that left its source when the universe was only about 3 billion years old, roughly a fifth of its current age. At that distance range, the map changed. A section of sky spanning the constellations Hercules and Corona Borealis was packed with gamma-ray bursts, not slightly elevated, not a gentle statistical bump, packed. Picture what a uniform map of these explosions should look like. If you scatter points randomly across a sphere, you expect rough evenness, some small clusters here and there, the way random noise always looks a little clumpy up close. What you do not expect is a dense concentration covering a substantial arc of the sky, sitting against a background that shows nothing comparable anywhere else in the same distance slice. That is what the team was looking at, a patch of sky that was clearly, dramatically different from everything around it. The first instinct in that situation is not excitement, it is suspicion. Horváth and his colleagues knew immediately that before they could say anything meaningful about the universe, they had to rule out themselves. Was the Swift satellite observing certain parts of the sky more than others? Were there biases in which bursts received optical follow-up, which is what produces the redshift measurements needed to place them at a specific distance? Were there systematic differences in how the ground-based telescopes had been operating during the period the data covered? These are not exotic concerns. They are the standard checklist for any anomaly in survey data, and they had to be worked through carefully before the result meant anything at all. They worked through it. The clustering survived, adjusting for known observational biases in the Swift catalogue, restricting the sample to bursts with the most reliable redshift measurements. checking whether the concentration held up when the analysis was approached from different angles. Each test left the signal standing. Something in that region of sky at that distance was genuinely overdense. The team could not make it disappear. What they had found spanned roughly 10 billion light-years in its longest dimension, 7 billion wide, nearly a billion light-years deep. Those numbers were already hard to absorb in isolation. In context, they were staggering. The previous record for the largest known structure in the observable universe stood at just under 4 billion light-years. This was more than twice that. It was nearly 8 times the size of the Sloan Great Wall, which had itself been considered astonishing when it was announced. The clustering signal in that single redshift band was pointing at something so large that the comparison to anything previously known felt almost meaningless. The team published their findings in November 2013. The structure needed a name. In astronomy, naming rights for a discovery typically belong to the people who made it, but occasionally a name emerges from somewhere unexpected. In this case, the name came from a Filipino teenager named Yondrik Valdez, who had been following the astronomical literature and aspired to become an astronomer. He proposed the name Hercules-Corona Borealis Great Wall, drawing on the constellations that mark the region of sky where the overdensity sits. The name stuck. It carries something of the old tradition of naming the sky's features after patterns humans drew in the stars, except that what the name now points at is not a handful of stars arranged in a shape. It is the largest known object in the universe. News of the discovery moved quickly through the astronomical community, and the reaction was not uniform. Some researchers found the signal compelling. Others were more cautious, pointing immediately to the limitations of gamma-ray burst data as a tool for mapping large-scale structure. The SWIFT satellite had not been designed as a cosmological survey instrument. Its burst catalogue was a byproduct of a mission aimed at understanding the explosions themselves, not at mapping matter distribution across the universe. The data it produced was real, but it was also uneven, assembled over years of observations with varying conditions, varying sky coverage, and varying availability of the follow-up observations needed to measure redshifts. Whether that unevenness could produce a false clustering signal was a question that could not be answered quickly. The implications, if the structure was genuine, were profound. Current models of structure formation suggested a universe where large structures grew through gravitational attraction over cosmic time. Something this size, at this distance, presented a significant challenge to existing theory. If confirmed, it would mean the observable universe contained at least one structure so vast that it approached theoretical limits of what could coherently exist given the universe's age and expansion rate. These were not minor complications. They were fundamental problems that could require new physics or a complete rethinking of how cosmic structures assembled themselves. The stakes of verification had become clear to the entire astronomical community. What the team had done was find something. Whether that something was a genuine physical structure or an artifact of how the data had been collected was a separate question entirely. The discovery and the verification were two different problems, and the announcement in 2013 only resolved the first one. The second was going to take years, different teams, different methods, and a great deal of argument. What nobody disputed was that the signal was there in the data. What it meant, and what it was, had not been settled. The question now was whether what they were looking at was real. When the team laid out the positions of the gamma-ray bursts in that particular redshift band and looked at where they fell on the sky, what came back was not what a smooth, evenly distributed universe should produce. Think about what a uniform distribution looks like. If gamma-ray bursts are scattered randomly across the sky, the way you would expect from a universe with no large structures at the scale being surveyed, the dots on the map should look roughly even. Some patches will have slightly more, some slightly fewer, the way raindrops falling on a sidewalk are not perfectly spaced, but still spread out. What you should not see is a dense, obvious clump concentrated in one region with the surrounding area conspicuously emptier. That is not random. That is a signal. The signal was there. It was hard to miss. At the redshift range the team was examining, corresponding to a slice of the universe roughly 10 billion light-years from Earth, the gamma-ray bursts were not behaving randomly. They were piling up. The overdensity was not subtle. In the region of sky covering the constellations Hercules-Corona Borealis, the concentration of gamma-ray bursts ran significantly higher than the surrounding background. The team ran the statistics. Under their analysis, the probability of that clustering appearing by chance in a genuinely uniform distribution was less than 1 in 1,000. Some estimates put it closer to less than 1 in 2,000. Numbers like that do not mean impossible. They mean that if you ran this survey 1,000 times on a truly random universe, you would almost never see something this concentrated in this small A patch of sky. The angular footprint of the overdensity was not small either. It did not confine itself neatly to 2 constellations. The clustering extended outward, spreading toward Boötes in one direction and toward Gemini in another. The full angular extent of the dense region covered a substantial arc of the northern sky. That angular size, combined with the distance, is where the physical dimensions started to become staggering. Distance turns angular size into actual size. When you are measuring something 10 billion light-years away, even a moderate angular span corresponds to an almost incomprehensible physical width. The team worked through the numbers. Along its longest dimension, the structure measured approximately 10 billion light-years across. That is not a typo. 10 billion light-years. In the perpendicular direction, its width measured roughly 7.2 billion light-years. Its depth, the extent along the line of sight, ran close to 1 billion light-years. This is not a flat sheet. It is not a 2-dimensional wall in any meaningful sense. It has substantial 3-dimensional volume. A depth of nearly 1 billion light-years means the structure has real thickness. You are not looking at a cosmic pancake. You are looking at something more like an enormous dense region of space, with mass and extent in every direction. To get a feel for what those numbers mean, consider the Milky Way. Our galaxy stretches roughly 100,000 light-years from edge to edge. That feels enormous when you are thinking about it in human terms. Light traveling for 100,000 years just across from one side to the other. Now try to place that galaxy against the length of this structure. To span 10 billion light-years by lining up Milky Way galaxies side by side, you would need roughly 94,000 of them. Not 94, not 940, 94,000 galaxies, each one 100,000 light-years wide, placed end to end before you reach the other side. The original paper included exactly that comparison, and it does not get easier to absorb no matter how many times you read it. Now hold the width in your mind alongside the observable universe. The full sphere of the observable universe, everything humanity has ever been able to see or detect or infer, extends roughly 93 billion light-years in diameter. The structure found in that data runs 10 billion light-years along its longest axis. That is more than 1/10 of the entire observable universe spanned by a single coherent overdensity. If you shrank the observable universe down to the size of a standard classroom, this structure would stretch across more than one full wall, floor to ceiling, corner to corner. Something worth understanding is what the team was actually measuring. They were not looking at a picture of this structure. They were looking at a statistical excess in the positions of gamma-ray bursts. An overdensity in a distribution is not the same as a photograph. What it means is that something in that region of the universe caused more massive stars to form and explode than you would expect if matter were spread evenly. More explosions in a given region means more matter. More matter means structure. The team was reading the skeleton of something enormous from the footprints it left in the death counts of distant stars. That is a remarkable piece of inference. The extent of the structure was striking enough on its own. What compounded it was the depth. A depth of nearly 1 billion light years is not a thin coincidence of alignment. When objects at similar distances pile up across a broad sky region, one possible explanation is that separate, unrelated structures happen to sit at similar distances and overlap in projection. But 1 billion light-year depth makes that explanation difficult to sustain. Objects 1 billion light-years apart in depth are genuinely separated in space. They're not casually superimposed. Something had to account for why that entire volume was denser than the surrounding regions at the same distance. The team was not claiming a thin wall seen face-on. They were claiming a thick three-dimensional excess of matter, spanning billions of light-years in every direction. Put all of those dimensions together, and the conclusion is not ambiguous. The structure being described was the largest discrete thing anyone had ever proposed existed anywhere in the observable universe. Nothing in the catalogue of known cosmic structures came close. A cluster of that size, if genuine, would be the largest thing anyone had ever found. To understand why the numbers stopped the astronomical community cold, you need to know what had been considered large before 2013. Astronomy has a habit of humbling itself. Every generation of researchers draws a mental map of the universe, decides where the edges of things are, and then watches a new instrument or a new survey erase those edges. Large-scale structure is where this pattern has played out most dramatically. The story of how big the universe's biggest features are is not a story of gradual refinement. It is a story of repeated shocks, each one arriving before the field had fully absorbed the last. The first chapter starts in 1989. Margaret Geller and John Huchera were mapping the positions of thousands of galaxies, building one of the first real three-dimensional pictures of the nearby universe. What came back from that survey was not what most astronomers expected. Instead of a roughly uniform scattering of galaxies, the map showed something long and coherent, a sheet of galaxies stretching roughly 500 million light-years across. They called it the Great Wall. Nothing that large had been identified before. The reaction was not uniform excitement. Some researchers thought the feature was genuine. Others argued it was an artifact of the survey's geometry, a boundary effect, something that would dissolve if you extended the map far enough in the right direction. The debate had that particular texture that shows up whenever a discovery is both surprising and hard to immediately confirm. But the structure did not dissolve. It stayed in the data. 500 million light-years is a number that does not announce itself well. It needs a frame of reference. The Milky Way is roughly 100,000 light-years across. The distance to the Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years. The distance to the nearest significant galaxy cluster is tens of millions of light-years. 500 million light-years is 5,000 times the diameter of the galaxy you live in. That was the Great Wall. The field absorbed it, eventually, and moved on. Then, in 2005, a team analyzing data from the Sloan Digital Sky Survey found something bigger. The Sloan Great Wall came in at 1.37 billion light-years in length, nearly 3 times the size of the Geller-Huchera structure. It stretched across a much larger slice of sky than anything previously catalogued. It held the record for nearly a decade, 1 billion light-years plus. The field absorbed this too, not without debate, but eventually it settled into the textbooks as the largest confirmed structure in the universe. For 10 years that designation stuck. Here is something worth noticing about that progression. Each record holder was not just incrementally larger than the previous one. Going from the Great Wall to the Sloan Great Wall meant nearly tripling the size of the largest known structure in the span of about 15 years. That is not gradual refinement. That is the survey getting deeper and wider and revealing something the older surveys could not reach. It raised an uncomfortable background question, one that most researchers preferred not to press too hard, which was whether the records would keep falling as the surveys kept improving. In 2012, they fell again. A team led by Roger Claus announced the Huge Large Quasar Group, a clustering of 73 quasars spread across a region roughly 4 billion light-years, in its longest dimension. Quasars are the extremely luminous cores of distant galaxies, powered by supermassive black holes, consuming enormous amounts of material. They can be seen from much farther away than ordinary galaxies, which makes them useful for mapping structure at greater depths. The huge LQG was 3 times larger than the Sloan Great Wall. It arrived in the literature like a stone thrown into still water. Reactions ranged from fascination to outright skepticism. Some researchers argued that quasar groups are not the same kind of structure as a galaxy wall, that they are looser and less physically coherent, and that calling the huge LQG a single structure was a question of definition as much as observation. Others pointed out that even accounting for those objections, the clustering was real and the scale was difficult to explain away. The huge LQG controversy had barely settled into a low simmer when the 2013 results arrived. The Hercules-Corona Borealis Great Wall was not found through galaxy surveys or quasar catalogues. It came from a completely different kind of observation, which made direct comparisons slightly complicated. But the size was not complicated at all. 10 billion light-years in its longest dimension, 7 billion wide, nearly a billion thick, against the previous record of 4 billion light-years. That number does not feel like a new entry in the same list. It feels like a different list entirely. Put it in plain terms. The Sloan Great Wall, which had held the record for a decade, measured 1.37 billion light-years across. The Hercules-Corona Borealis Great Wall measured roughly 10 billion. That is not 10 or 20% larger. It is almost 8 times larger. The huge LQG, which was already controversial for being too big to sit comfortably in standard models, measured about 4 billion light-years. The Hercules-Corona Borealis Great Wall was more than twice that size. The community had spent years debating whether a 4 billion light-year structure could be real. Now there was a structure claiming to be 10 billion, found through a different method, in a different kind of data, at a different depth in the universe. The pattern of shock and absorption that had played out with the Great Wall and the Sloan Great Wall had always involved some time to process. Each new record arrived, triggered debate, and eventually settled into the accepted picture. What made 2013 different was the size of the gap. You could plausibly trace a line of discovery from 500 million to 1.37 billion to 4 billion and tell a story of gradual expansion. You could not easily extend that line to 10 billion without stopping to ask whether something was fundamentally wrong with the picture. The Hercules-Corona Borealis Great Wall was not slightly bigger than these previous record holders. It was several times larger, and that gap was exactly the problem. At the heart of modern cosmology is an assumption so fundamental that most of the people working in the field barely stop to examine it consciously. It does not have a dramatic name. It does not come with a story of its discovery. It is simply called the cosmological principle, and it says that the universe, smoothed out over large enough scales, is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. If you could take a big enough chunk of the universe and compare it to any other chunk of the same size, they would look essentially identical. No special places, no special directions, everywhere, roughly, equal. That idea did not come from a single observation or a single experiment. It came from something older and more philosophical. When Copernicus argued that Earth was not the center of the solar system, he was making a claim that went beyond orbital mechanics. He was saying that we are not special, that the place we happen to occupy does not hold a privileged position in the structure of things. Astronomers inherited that logic and applied it to the universe itself. If you follow it to its conclusion, it tells you that any sufficiently large piece of the cosmos should be representative of the whole. No region should be dramatically richer or emptier than any other once you zoom out far enough. That is the Copernican argument extended to its limit, and it became the philosophical backbone of modern cosmology. It is not just philosophy, though. The cosmological principle has evidence behind it. The most powerful piece of that evidence is the cosmic microwave background. This is the faint glow of radiation left over from the early universe, about 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and light to travel freely for the first time. When you map this radiation across the entire sky, it is extraordinarily uniform. The temperature barely varies by more than 1 part in 100,000 from one region to the next. That smoothness is not an accident. It is exactly what you expect from a universe that started homogeneous and has stayed broadly homogeneous ever since. The cosmic microwave background is one of the most precisely measured things in all of science, and it tells you in the most direct terms possible that the early universe was not lumpy in any dramatic way. The standard cosmological model, known as Lambda-CDM, is built directly on top of this principle. Lambda refers to the cosmological constant, which drives the accelerating expansion of the universe. CDM stands for cold dark matter. Together, they form a framework that has been stunningly successful. It correctly predicts the large-scale distribution of galaxies. It accounts for the observed abundance of light elements. It matches the precise details of the microwave background's temperature fluctuations. Every major observational test that astronomers have thrown at it over the past few decades has come back more or less confirming the model. That is an extraordinary track record. And the cosmological principle is not a peripheral assumption in that model. It is the foundation. Pull it out and the entire mathematical structure built on top of it requires rethinking from the ground up. So the question becomes practical. At what scale does the principle actually hold? At the scale of a single galaxy, the universe is obviously not homogeneous. Galaxies are dense. The space between them is nearly empty. At the scale of galaxy clusters, still not homogeneous. Clusters are denser than the voids surrounding them. At the scale of superclusters and filaments, still lumpy. The cosmic web, with all its threads and nodes and enormous empty spaces, is visibly structured. But cosmologists have expected all of this to average out above a certain threshold. Run the numbers on the standard model, and you get a prediction. Somewhere around 300 to 400 million light years, the universe should stop looking structured and start looking smooth. Above that scale, any large cube of space U, SAM, please should contain roughly the same density of matter as any other large cube. The lumps wash out. The web fades into a uniform background. This is what most of the field has taken as the working answer to the question. 3 to 400 million light years is the scale of homogeneity. Below it, structure exists and is expected. Above it, the universe irons itself flat. And when you look at the data from galaxy surveys on those scales, this is broadly what you see. The largest known structures before the Hercules-Corona Borealis Great Wall fell in the range of 1 to 4 billion light-years, which already stretched the expectation uncomfortably. But they were debated, they were absorbed, and the model survived. Now here is the problem. Standard inflationary models, which describe the very first moments of the universe's existence, make a specific prediction about how large coherent structures can get. Inflation was a period of extraordinarily rapid expansion in the first fractions of a second after the Big Bang. It stretched quantum-scale fluctuations to cosmological sizes, seeding the density variations that would eventually grow into everything you see when you look at the night sky. Those fluctuations had a particular statistical character, and that character places a hard ceiling on the size of structures that gravity can assemble from them. Most calculations put that ceiling at roughly 1.2 billion light-years. That is not a round number chosen for convenience. It falls out of the mathematics of how inflationary perturbations evolve. The Sloan Great Wall at 1.37 billion light-years was already nudging that boundary. That made people uncomfortable. But 1.37 billion is close enough to 1.2 billion that you could argue the models were still roughly right. You could accommodate it with some adjustment at the margins. What you cannot accommodate with a margin adjustment is a structure 10 billion light-years across. That is not a small violation of the boundary. It is a violation by nearly an order of magnitude. A structure that large cannot grow out of the density fluctuations that inflation is supposed to have produced. The initial conditions required to form something so coherent across such a vast scale are not consistent with the smooth, nearly uniform early universe that the microwave background shows us. For both things to be true simultaneously, something in the picture has to be wrong. That is what makes this discovery so uncomfortable for theoretical cosmology. It is not that the Hercules-Corona Borealis Great Wall is merely large. It is that its existence, if confirmed, demands an explanation that the standard framework does not currently provide. The Hercules-Corona Borealis Great Wall, if it is real, sits well outside the scale where homogeneity is supposed to have taken hold, and that is not a comfortable place for something to sit. Not everyone accepted the discovery. The reaction inside the astronomical community was not simple amazement. It was complicated, fractured, and in some corners genuinely hostile, not toward the researchers personally, but toward the claim itself. A structure 10 billion light-years across sits so far outside the boundaries of what the standard model permits that accepting it at face value would mean accepting that something fundamental about cosmology is broken. For a field built on the cosmological principle, that is not a small concession. The first wave of skepticism came from theorists. If the universe is supposed to be homogeneous above roughly 300 to 400 million light-years, then a coherent structure 10 billion light-years long is not just an outlier, it is a different category of object entirely. Some researchers pointed out that no known physical mechanism could plausibly organize matter on that scale in the time the universe has had to work with. Gravity builds structure, but it builds it slowly, seeding small overdensities and growing them over billions of years into filaments, walls, and clusters. To produce something the size of the Hercules-Corona Borealis Great Wall, through ordinary gravitational collapse would require initial conditions that the Big Bang simply does not appear to have provided. Were the observations correct, or was the interpretation the problem? But the deeper and more pointed criticism was not about the physics. It was about the tool. Gamma-ray bursts are not galaxy surveys, and that difference matters more than it might first appear. A galaxy survey maps the sky by detecting light from millions of galaxies, using carefully characterized instruments with well-understood selection effects. The surveys are designed from the start to be as uniform as possible. GRB catalogs are built from nothing like that process. A gamma-ray burst is detected when a satellite happens to be looking in the right direction at the right moment, and when the burst is bright enough to cross the detection threshold of whichever instrument is operating at the time. That last part is important. Different satellites have different sensitivities. NASA's Swift Gamma-ray Burst mission was the primary source of the data behind this discovery, but the catalogue also incorporated observations from other instruments and ground-based optical telescopes used to measure redshifts from afterglows. Each of those instruments has its own observing history, its own biases, its own gaps. Swift does not stare at one part of the sky. It sweeps, responds to triggers, and follows up on alerts. Its coverage is episodic and uneven. Some regions of the sky simply accumulate more burst detections over time because of how the satellite's orbit and pointing history interact with what happens to be out there. Others are systematically undersampled. What this means in practice is that the raw number of gamma-ray bursts detected in any patch of sky is not a clean measurement of how many gamma-ray bursts actually occurred there. It is a measurement of how many bursts occurred there and were detectable by the instruments that were running and were bright enough to trigger the detectors and were followed up quickly enough to get a redshift. Each of those filters introduces a potential bias, and if those biases happen to concentrate detections in one region of the sky at one range of redshifts, the result can look like a genuine overdensity even when the underlying distribution of gamma-ray bursts is perfectly uniform. This is what skeptics called observer bias, and the concern was specific. At a redshift of around 2, the ability to measure a reliable redshift from a burst's optical afterglow depends heavily on whether ground-based telescopes could respond quickly enough after the initial detection. That response time is not uniform around the sky. Some observatories are better positioned to catch afterglows from certain sky regions. Others have gaps in their coverage. If the Hercules-Corona Borealis region happened to be better covered by follow-up telescopes during the period of the survey, more bursts in that region would accumulate confirmed redshifts. More confirmed redshifts means more data points. More data points in one patch of sky looks exactly like a clustering signal. The researchers who raised these concerns were not dismissing the work. Most of them acknowledged that the original team had done careful analysis, had cross-checked their results, and had tried to account for known biases. The dispute was about whether the accounting had gone far enough. It is genuinely difficult to correct for selection effects you cannot fully characterize. Some of the biases built into GRB catalogs are well understood and can be modeled. Others are subtle, buried in the specific history of how each instrument operated and how follow-up campaigns were coordinated across different facilities over more than a decade. Digging all of that out and removing its fingerprint from the data is not straightforward. Reasonable people can look at the same catalogue and disagree about whether the corrections applied were sufficient. There was also a quieter question running underneath all of this. Even setting aside the observational concerns, what would it mean for a structure this large to exist? If you accept the Hercules-Corona Borealis Great Wall as a genuine physical object, you are not just adding a new entry to the record books. You are acknowledging that the universe organized itself on a scale where the standard model says organization should not be possible. That is not a conclusion most cosmologists reach easily. The cosmological principle is not a minor convenience. It is the scaffolding that holds together almost every major result in modern cosmology. Pulling it loose at 10 billion light-years has consequences that ripple through decades of theory. So the mood in the field was something like cautious refusal. Not rejection, not acceptance, but a sustained demand for a higher standard of evidence before anyone was prepared to start rewriting the textbooks. The data was interesting. The signal was real in some sense, but whether it pointed at a genuine physical structure or at the imperfect fingerprint of how the survey was assembled, that remained an open question. What researchers needed was not more argument from either side, but better data, and that had not yet arrived. The core of the scientific dispute came down to something that sounds dry and technical, but turns out to be genuinely consequential. The original team placed the probability of the observed clustering happening by random chance at less than 0.1%. That is a number that sounds decisive. In most scientific contexts, a result that's strong would end the argument. You found something. Move on. But critics looked at how that number was calculated and argued the methodology had buried several assumptions that, once pulled into the open, changed everything. The debate that followed was not about whether the data existed. The data existed. It was about what the data actually meant, and that turned out to be a much harder question. Here is where the numbers came from. When you want to test whether a cluster of objects is real, you compare what you observed to what you would expect from a uniform, random distribution. The gap between those two things is your signal. The bigger the gap, the less likely it is that chance produced it. This sounds straightforward. The problem is that the expected background is not something you measure directly. You calculate it, and the way you calculate it depends on choices that are not written in the laws of physics. They are judgment calls. How large a region of sky do you use to define the background? Which redshift range do you include? How do you weight bursts from regions of sky with better or worse observational coverage? Each of these decisions shifts the baseline. Shift the bar DARS, Selene, and the gap between expected and observed changes. Change the gap, and the probability changes with it. The 2015 critical paper zeroed in on exactly this problem. The authors argued that the original analysis had used a method for estimating the background distribution that did not properly account for non-uniform sky coverage. Gamma-ray burst surveys are not clean. Different parts of the sky have been watched more carefully than others. Some regions have dense observational histories going back years. Others are sparsely sampled. If you calculate your expected background assuming uniform coverage, and the actual coverage was not uniform, your signal can look stronger than it really is. Patches of sky that were observed more often will naturally contain more detected bursts. That is not clustering. That is just telescope time. The critics recalculated. After correcting for what they saw as these methodological problems, the probability of the clustering occurring by chance came out somewhere between 5 and 20%, not less than a fraction of a percent, between 5 and 20. That range does not sound like a discovery. That range sounds like noise you cannot explain yet. It is the kind of number that makes scientists shrug and ask for more data, rather than call a press conference. What makes this genuinely difficult is that neither side was wrong in any simple sense. The original team had made defensible choices. The critics had made equally defensible corrections. The disagreement was not about arithmetic. It was about what the right setup for the problem actually was. You can think of it like measuring the temperature in a room. If you hold the thermometer near a window, you get one number. If you hold it in the center of the room, you get another. Both numbers are accurate. Which one represents the room depends on what you are trying to measure, and that question requires judgment that the thermometer itself cannot answer. The redshift bin choice was another fault line. The original analysis concentrated on bursts at a particular redshift range, roughly z equals 2, where the clustering appeared strongest. Critics pointed out that if you go looking for clustering in a specific slice of the universe, and then calculate how unlikely that clustering is without accounting for the fact that you chose that slice because it looked unusual, you are going to underestimate the probability of finding something by chance. Statisticians call this the look elsewhere effect. It is the same problem that makes it easy to find patterns in random data when you are free to search wherever you want and only report what you found. The original team disputed the severity of this concern in their specific case, but the point was legitimate enough that it could not simply be waved away. The original researchers responded to the criticism carefully. They stood behind their methodology. They had not, in their view, made the errors they were being accused of. They had considered sky coverage. They had not simply mined the data for the strongest signal, without accounting for the search, but they also acknowledged that the uncertainties were real. This is what honest science looks like when the data is imperfect. You defend what you did while recognizing that reasonable people, looking at the same data set, are going to arrive at different answers depending on the choices they make. Neither side was being reckless. Both sides were wrestling with the genuine difficulty of extracting a clean signal from a messy, incomplete, human-assembled sea catalog. of cosmic explosions. What it came down to was this. A probability below 0.1% tells you the universe almost certainly contains a real structure. A probability of 15% tells you the universe might contain a real structure, or you might just be looking at an imperfect dataset from an unlucky angle. These are not the same conclusion. The entire scientific weight of the discovery pivots on which of those numbers is closer to the truth. And the answer depends on statistical choices that the data itself cannot adjudicate. That is the situation the field was left in. Not fraud, not error, not a failure of imagination. Just a set of legitimate, unresolved technical disagreements about how to handle data that was never designed to answer this specific question. The clustering was there, whether it meant something real, or whether it was an artifact of how the sky had been watched, remained genuinely open. In science, a disagreement this sustained, without a clean resolution, is often where the most important work eventually happens. While the critics were making their arguments, separate groups of researchers went back to the same data with different methods and found the same thing. This is worth pausing on, because it matters how science actually works here. When a single team produces a single result using a single method, skepticism is the correct response. One set of hands, one set of choices, one chance for something to go subtly wrong. What changes the picture is independent confirmation. Different teams, different tools, different assumptions, and if they all keep landing in the same place, that is no longer a methodology story. That is starting to look like a real signal. Several groups took that exact approach. They pulled the gamma-ray burst catalogs, applied their own statistical frameworks, went looking for the overdensity the original team had reported. Some used nearest neighbor tests, comparing the distance between observed bursts to what a random distribution would produce. Others used angular correlation functions that measure whether bursts at similar redshifts cluster together more tightly than expected across the sky. These are not small variations on the same method. They are fundamentally different ways of asking the same question, and they kept returning the same answer. Something in that region of the sky was denser than background. The clustering was there. What made this striking was not just that the signal survived a different test, it was that the signal survived attempts to break it. Researchers tried restricting the sample to only the brightest gamma-ray bursts, the ones most reliably detected regardless of which satellite happened to be watching. The clustering was still there. They tried the opposite, dropping the brightest events and keeping only the moderate ones, reducing the influence of any particularly dramatic outliers. Still there. They looked at subsets based on the quality of the redshift measurement, keeping only the bursts whose distances were most precisely known and discarding the ambiguous cases. Still there. Each time someone tightened the sample in a way that should have weakened a statistical artifact, the clustering, held. That pattern is exactly what distinguishes a real physical structure from an observational bias. A sampling artifact is fragile. It depends on the specific quirks of the dataset that produced it, the particular satellites involved, the particular sky coverage gaps, the particular years of observation. Pull on it in the right way, restrict the sample, change the selection criteria. It tends to fall apart. A genuine overdensity in the distribution of matter does not care how you slice the catalogue. It is there because the matter is there, and no amount of methodological pruning makes it disappear. One group pushed further and looked at whether the angular shape of the overdensity was consistent across different statistical approaches. The original team had described a region spanning roughly the constellations Hercules and Corona Borealis, but extending in the angular direction toward Boötes and Gemini as well. When independent researchers mapped the overdensity using their own boundary definitions, they were not drawing identical outlines, but the core of the excess, The region where the gamma-ray burst density was highest relative to background came back in essentially the same part of the sky. The shape was not perfectly reproducible because different methods define edges differently, but the center held. This is not the same as proof. It has to be said plainly. None of these independent analyses close the case. The core uncertainty, whether gamma-ray burst surveys are uniform enough to support this kind of structural inference at all, did not evaporate because multiple teams found the same clustering. If there is a systematic bias baked into the catalogs themselves, independent teams working from those same catalogs will reproduce it faithfully. Finding the same pattern in the same flawed dataset is better than finding it once, but it is not the same as finding it in a completely independent dataset collected through a different method entirely. That test has not yet been run in any definitive way. Still, robustness under this kind of pressure is significant. The researchers who remained skeptical after 2013 had argued that the original analysis was fragile, that specific choices made by the original team were doing the heavy lifting, that different reasonable choices would make the signal weaker or disappear entirely. What the follow-up analyses showed was that this was not quite right. The choices mattered at the margins. Different methods gave somewhat different estimates of the structure's boundaries and significance, but none of them gave nothing. The absence of the result under independent scrutiny, which is what you would expect if the original detection was a statistical artifact tied to one team's particular approach, did not materialize. One analysis took a particularly careful look at the redshift range involved. The original detection had concentrated on a specific band around Z is approximately equal to 2. Researchers asked whether the clustering was genuinely confined to that range, or whether it was bleeding into adjacent redshift bins in a way that suggested edge effects from the statistical window used. What they found was that the overdensity did have some extension beyond the original reported range, which some took as evidence for a broader structure. Others took as a reason to question whether the boundaries had been defined correctly in the first place. What it did not look like was a clean artifact sitting neatly at the edges of a redshift bin and vanishing the moment you looked outside it, either middle of the decade following the discovery. The scientific situation had reached a state that is both uncomfortable and genuinely interesting. The skeptics had made real points. The statistical debate had not resolved cleanly in the original team's favor. The methodological concerns about GRB surveys as structural traces remained legitimate and unresolved. But the signal had also proven more durable than a fragile artifact should be. Multiple teams had handled it, tested it, restricted it, and tried to make it go away. It had not gone away. What this suggested, and what made some of the skeptics quieter than they had been, was that the clustering was not going away under pressure. A lot of the confusion around this discovery traces back to a question most people have never had reason to think about. How do astronomers know how far away a gamma-ray burst actually is? These explosions happen in an instant. They leave no address. There is no ruler you can stretch across 10 billion light-years. The answer is redshift. And once you understand what redshift is, the whole architecture of this discovery starts to make more sense. Start with the universe expanding. Every galaxy is moving away from every other galaxy, not because the galaxies themselves are flying outward through space like shrapnel, but because the space between them is stretching. The fabric itself is growing. Light traveling through that stretching space gets stretched along with it. Its wavelength increases, and when a wavelength increases, the light shifts toward the red end of the visible spectrum. That shift is the redshift. The longer the light has been traveling, the more the universe has expanded around it, and the more its wavelength has been pulled apart. So, a high redshift tells you the light is old, and old light means distant source. This is not a metaphor. It is a direct physical consequence of living inside an expanding universe. The light does not know it is being stretched. It just travels, and the space it travels through keeps getting bigger, and by the time it reaches your detector, it carries a record of exactly how much expansion it lived through. That record is readable. That is the key thing. Astronomers can open that record and extract a number. Here is how they do it in practice. Every element in the periodic table absorbs and emits light at specific wavelengths. Hydrogen absorbs at one precise set of wavelengths, oxygen at another, magnesium at another. These are fixed, laboratory measured values. They do not change. When a gamma ray burst goes off and leaves behind a glowing afterglow, that afterglow shines through whatever gas and dust exists along the line of sight, and those elements leave their fingerprints in the spectrum, absorbing light at their characteristic wavelengths. An astronomer points a telescope at the afterglow, breaks the light into its component wavelengths, and looks for those fingerprints. The fingerprints are there, but they are not at the wavelengths the laboratory says they should be. They are shifted. Move toward the red. The size of that shift is the redshift value, written as Z. Measure the shift, calculate Z, and you have a distance. This sounds straightforward, but the window for doing it is narrow. Gamma ray bursts fade fast, hours, sometimes less. Ground-based telescopes have to pivot quickly after a satellite alert, before the afterglow disappears entirely. Not every burst gets a measured redshift. Some are too faint. Some set before their host galaxy is above the horizon clacks. Some simply fade before anyone can get a spectrum. This is one of the reasons GRB surveys are not perfectly uniform, and it feeds directly into the statistical debates around the Hercules-Corona Borealis Great Wall. Redshift coverage is uneven, and uneven coverage creates headaches when you are trying to decide whether a clustering signal is real. The Hercules-Corona Borealis Great Wall sits at roughly z=2. That number requires some unpacking. The universe today is roughly 13.8 billion years old. A redshift of 2 corresponds to a look-back time of about 10 to 11 billion years. The light arriving from those gamma-ray bursts left its source when the universe was somewhere around 3 billion years old, roughly a fifth of its current age. The universe at that point was physically smaller, hotter, and denser. Galaxies were forming aggressively. Star formation rates were near their peak. The conditions were nothing like what surrounds us now. What this means for the structure itself is significant. When astronomers say the Hercules-Corona Borealis Great Wall is 10 billion light-years across, they are not describing something that exists in the present. They are describing a pattern in the distribution of ancient explosions, a snapshot of where matter was concentrated at a specific moment in cosmic history. The structure, if real, existed then. Whether anything coherent remains in that region today, whether it has merged, dispersed, evolved into something unrecognizable, is a separate question that the data cannot answer. You are looking at a fossil arrangement, not a living one. This is worth sitting with for a moment. Every observation in astronomy is observation of the past. The sun you see in the sky is 8 minutes old. The Andromeda galaxy you can barely make out on a dark night is 2.5 million years old. At z=2, the delay is measured in billions of years. The universe that produced those gamma-ray bursts was so different from the one we inhabit that it barely resembles the same place. And yet the light still carries the information. The expansion of space encoded itself into the spectrum of each burst, and modern instruments can read that encoding with enough precision to place each explosion at a specific distance and a specific moment in time. This is also why the statistical analysis is so demanding. Building a three-dimensional map from redshift data requires combining position on the sky, which is straightforward, with distance estimated from redshift, which depends on a cosmological model. The model connects Z to physical distance using parameters like the Hubble constant and the density of dark matter and dark energy. If those parameters shift slightly, every distance in the map shifts with them. The structure does not disappear, but its exact dimensions depend on choices about cosmology that are themselves still being refined. Every distance in that map is a calculation, not a direct measurement, and every calculation rests on a model of the universe that is still being tested. Every gamma-ray burst in that survey is a fossil signal from an explosion that happened billions of years ago, arriving at our instruments with the entire history of an expanding universe baked into its spectrum. Standard cosmological models make a specific prediction about the largest structures that should exist in the universe, and it is a prediction that can be calculated precisely. That is what makes this particular problem so hard to dismiss. This is not a case where theorists shrug and say the models are vague. The models are specific. They give you a number, and the number the Hercules-Corona Borealis Great Wall comes back with is so far outside what the models allow that the gap is difficult to look at without stopping to ask what it means. To understand why, you have to go back to a fraction of a second after the Big Bang, when something happened to the universe that set the rules for everything that came after it. The event is called inflation. In the first unimaginably brief interval after the Big Bang, fractions of a second so small that normal language does not have useful words for them, the universe expanded at an extraordinary rate, not the ordinary expansion that continues today, but something far more violent, an exponential stretching of space that took whatever was there and smoothed it out across enormous scales. Think of a wrinkled sheet being pulled flat in every direction simultaneously, fast enough that any large-scale clumping in the original distribution gets erased. That is roughly what inflation did to the early universe. It took the initial conditions and ironed them out, leaving behind something close to uniform. What it did not erase were tiny quantum fluctuations, microscopic ripples in the density of energy that inflation stretched and preserved. Those tiny ripples became the seeds of everything that followed. Here is why those seeds matter. Once inflation ended and the universe began cooling, matter started gathering in the regions where those density fluctuations had left a slightly higher concentration of material. Gravity pulled more matter toward those overdense spots. Over hundreds of millions of years, and then billions, the overdensities grew. Galaxies formed in the denser regions. Clusters of galaxies formed where multiple overdensities were close enough to pull together. The filaments and walls of the cosmic web grew along the same lines. Every structure in the universe traces its ancestry back to those original quantum fluctuations. And because the fluctuations came from a specific physical process, inflation, they carry a specific statistical fingerprint. The spectrum of those fluctuations is not random. It follows rules that can be calculated and tested against observation. That spectrum has a ceiling built into it. The fluctuations that inflation produced were not equally powerful at all scales. On very large scales, the primordial variations in density were small enough that gravity could not pull together coherent structures above a certain size. The universe started too smooth at large scales for anything truly enormous to grow into a single bound or semi-bound object. Run the numbers through the standard inflationary framework, account for the rate of structure growth under gravity, factor in dark matter and dark energy, and what you get is a hard upper limit. Most careful calculations put the maximum expected size of a coherent large-scale structure at roughly 1.2 billion light-years. Above that threshold, the density variations are simply too weak and too uncorrelated to produce something you could point to and call a single structure. Now consider what already existed before 2013. The Sloan Great Wall, at roughly 1.37 billion light-years, was already sitting uncomfortably close to that boundary. Some researchers argued it was slightly over the line. Others contended that because it was not a gravitationally bound object, but a loose filamentary arrangement, the standard limit did not quite apply in the same way. The debate was real, and it had not fully resolved itself when the next discovery arrived. The huge large quasar group, at around 4 billion light-years, pushed the problem further. Each of these discoveries arrived at the edge of what the models were comfortable with, and each triggered a version of the same argument. Then the Hercules-Corona Borealis Great Wall entered the picture. At 10 billion light-years across, it is not nudging against the boundary. It is not slightly outside it. It is more than 8 times the size of the Sloan Great Wall, and roughly 2.5 times the size of the huge LQG. The 1.2 billion light-year ceiling is not a distant memory from this vantage point. It is not even visible in the rearview mirror. What would have to change for something this large to exist? There are a few possibilities, and none of them are comfortable. The first is that the primordial density fluctuations on these scales were significantly stronger than inflation predicts. If the initial seeds were larger, the resulting structures could in principle be larger too, but this would require a modification to inflationary theory that has no other observational support. The cosmic microwave background, which maps those primordial fluctuations in extraordinary detail, does not show the kind of enhanced power on large scales that this explanation would require. Changing inflation to accommodate the wall means breaking something else that the models currently get right. The second possibility is that structure grew faster under gravity than the standard model allows. Dark matter drives the growth of structure. If there was more of it in certain regions, or if it clustered differently than expected, maybe gravity had more to work with. But the scale of the discrepancy makes this hard to close. You would need an unusual concentration of dark matter on extraordinary scales, and there is no independent evidence for that either. The third possibility is something outside the current framework entirely, an unknown physical process operating on cosmological scales, something that is not dark matter, not dark energy as currently understood, not inflation as currently modeled, something new. Astronomers are cautious about invoking unknown physics without strong evidence, and reasonably so, but the absence of a clean explanation inside the existing framework is itself a signal worth taking seriously. When the best models fail to account for an observation by a factor of 8 or more, that is not a rounding error. That is a problem. What the Sloan Great Wall showed was that the models had limits. What the huge LQG showed was that those limits were being reached more often than expected. What the Hercules-Corona Borealis Great Wall showed was something different in kind. Not a structure that nudges against the theoretical ceiling, but one that, if it is real, stands so far outside that ceiling that no obvious path exists from the current framework to the observation. The gap cannot be closed by adjusting parameters. It cannot be explained away by pointing to measurement uncertainty. If the wall is real, it means the universe managed to construct something far larger than the standard recipe allows, and nobody has a clean explanation for how. One of the stranger developments in the story of the Hercules-Corona Borealis Great Wall is that subsequent analysis has not made it smaller. When a controversial discovery comes under sustained pressure from the scientific community, the usual outcome is one of two things. Either the signal fades under closer inspection and the original estimate shrinks, or the evidence collapses entirely. What happened here was neither. Researchers who went back to the gamma-ray burst catalogue with fresh methods and wider redshift windows did not find a smaller structure. They found a larger one. That outcome is strange enough that it is worth sitting with for a moment, because it changes the shape of the problem considerably. The original 2013 analysis placed the Hercules-Corona Borealis Great Wall at a redshift of roughly Z equals 2. That redshift corresponds to a time when the universe was about 3 billion years old, roughly a fifth of its current age. The structure appeared to occupy a relatively well-defined band in redshift space, concentrated around that value. That was already a staggering result. But subsequent work, including analyses published around 2020 and afterward, started finding that the overdense region did not stay neatly inside that band. It extended outward in both directions along the line of sight, reaching redshifts as low as roughly 0.33 and as high as roughly 2.43. Those are very different distances. The lower end of that range corresponds to a universe that is already several billion years old, meaning some of the structure's components are much closer to Earth than anyone initially suspected. The upper end pushes even deeper into the early universe than the original discovery had mapped. What does it mean to stretch the redshift range from 0.33 to 2.43? In physical terms, it is dramatic. A structure that was already 10 billion light-years across in its original estimate now appears to span a volume that, along its depth alone, covers an enormous fraction of cosmic history. The components closest to Earth sit in a universe that has had billions of years more time to evolve than the components at the far end of the range. If these are genuinely connected, the structure is not just physically enormous, it is cosmologically deep in a way that almost nothing else we have ever observed can match. The team conducting this reanalysis was explicit about one thing. The expansion of the apparent size did not look like a statistical fluctuation. It did not look like a sampling artifact. They went through the same checklist that had fueled the original debate: sky coverage biases, redshift measurement reliability, whether certain GRBs were easier to detect in certain redshift ranges, and the expanded signal survived those checks. The clustering was real enough in their analysis to remain standing after the standard pressure tests. What they also found was that the structure is not a single, clean, monolithic wall. The original name, the Great Wall, conjures an image of something unified and continuous, like a vast sheet of galaxies stretching in one direction. That picture is probably too simple. The reanalysis found evidence that the Hercules-Corona Borealis Great Wall encompasses several smaller, distinct overdense clusters. These clusters are not randomly scattered. They appear to be embedded within, or associated with, the broader overdense region rather than sitting outside it. Think of it less like a flat wall and more like a sponge with dense nodes connected by thinner threads, all of it sitting inside a region of space that is overall denser than its surroundings. This distinction matters for the physics. A single monolithic structure would require something specific, a coherent density enhancement that formed and evolved as a unit across a vast stretch of space. A complex of related overdensities is a different kind of object, and in some ways a more plausible one. Gravity works locally. It can build clusters. It can connect clusters along filaments. A hierarchy of overdense regions, each formed through its own history, but collectively concentrated in one region of the sky and one range of redshifts, is at least conceptually more approachable than a single uniform wall. But here is the catch. Even under this more complex interpretation, the overall region those clusters occupy is still enormous. The footprint does not shrink just because the intern. All structure is more complicated. In fact, a web of overdense clusters spread across an even wider redshift range occupies more volume, not less. This is the uncomfortable situation that the reanalysis left the field with. The debate had been partly framed around whether the original number, 10 billion light-years, was reliable. Critics had reasonable grounds to push back on that estimate, given the limitations of the data. But the subsequent work did not resolve the controversy by bringing the number down. It moved the number in the other direction. The region appears to be larger than originally reported, more complex in its internal structure, and it extends closer to Earth than anyone had initially measured. For cosmology, this progression is hard to absorb. Structures that start large and grow under additional scrutiny are structures that the standard models have an increasingly difficult time explaining away. The inflation argument, the one that places a hard ceiling of roughly 1.2 billion light-years on coherent cosmic structure, does not become more comfortable when the anomaly doubles in apparent size. It becomes less comfortable. Every additional billion light-years of extent, every additional cluster embedded in the system, adds to the difficulty of fitting the observation into the existing framework. The questions that surrounded the original discovery are still open. Whether the structure is real, whether it violates the cosmological principle, whether inflation needs revision, none of those questions has a settled answer. But the geometry of the problem has shifted. The thing being questioned is now bigger than it was. The structure that was already too large to fit comfortably into the models turned out, on closer inspection, to be larger still. The cleanest path to settling this debate runs through a telescope that does not exist yet. Every major argument about the Hercules-Corona Borealis Great Wall eventually circles back to the same problem. The data is imperfect. The GRB catalogues that revealed the clustering in the first place were built from observations gathered by multiple satellites operating across different years, each with its own sensitivity thresholds, its own sky coverage patterns, its own blind spots. SWIFT was never designed to map large-scale cosmic structure. It was designed to catch gamma-ray bursts fast and point other telescopes at them before the afterglow faded. That it produced data useful for structure mapping at all was a kind of fortunate accident. But fortunate accidents leave marks. The sample is uneven. Some patches of sky are better covered than others. Some redshift ranges are easier to follow up than others. These irregularities sit inside every analysis anyone has ever run on this dataset, and no amount of statistical correction fully removes them. You cannot correct for something you cannot fully characterize. This is where THESEUS comes in. The full name is the Transient High Energy Sky and Early Universe Surveyor. It is a proposed European Space Agency mission, and the whole point of it from the ground up is to do what SWIFT was never built to do. Detect gamma-ray bursts across a wider range of energies, cover the sky more uniformly, and critically, measure redshifts directly from the burst itself rather than waiting for ground-based telescopes to catch the afterglow at a random moment under whatever weather conditions happen to exist that night. THESEUS carries an onboard infrared telescope specifically for this purpose. Infrared light penetrates the dust and gas that can obscure the afterglows of distant bursts from optical telescopes. You get a redshift for more bursts, not just the ones that were bright enough and lucky enough to be followed up under good conditions. That last part matters more than it might sound. One of the persistent worries about the current GRB catalogues is that redshift measurements are not available for every burst in the sample. The bursts without confirmed redshifts have to be excluded from structure analyses or handled with statistical assumptions about where they might fall. Either way, you are working with an incomplete picture. A mission that delivers redshifts for a far higher fraction of detected bursts gives you something far more powerful. A sample where you actually know where things are, rather than inferring it. Think of what the current situation looks like from an engineer's standpoint. You want to know whether a signal in a dataset is real, or an artifact of your instrument. The most direct test is to build a better instrument, one whose biases you understand completely, and run the measurement again. If the signal survives a clean instrument, it was probably real. If it disappears, it was probably the old instrument talking to itself. That is exactly what THESEUS offers this particular problem. A single, well-characterized uniform survey from a single mission. No patchwork of satellite archives from different eras. No gaps in sky coverage that vary from year to year based on which observatories were operational. One dataset, built to a consistent standard, designed specifically to answer the kind of question the Hercules-Corona Borealis Great Wall is asking. Researchers directly involved in the original discovery have said this plainly. THESEUS is what the field needs to decide. That is not a vague hope about future technology. It is a specific statement about what the problem requires. The uncertainty is not coming from ambiguity in the physics or disagreement about theory. It is coming from the limitations of the data. Fix the data and the answer becomes legible. THESEUS is the fix. What would a definitive result actually look like? If the Hercules-Corona Borealis Great Wall is a genuine physical structure, a properly uniform GRB survey should detect it without ambiguity. The overdensity in that region of the sky at that redshift range should appear in the new data just as it appeared in the old, but cleaner, sharper, no longer dependent on statistical corrections that skeptics can dispute. The argument dies. The structure goes into the catalogue as real, and the theoretical headache of explaining it becomes the field's primary obligation. If the wall is an artifact, the reverse happens. A uniform survey with no selection effects should produce a distribution of gamma-ray bursts that looks roughly the way a smooth, homogeneous universe predicts. The clustering fades. The apparent Great Wall dissolves into background noise. The community moves on, somewhat relieved, and the cosmological principle survives intact at this scale. Either outcome is valuable. Science does not only advance by confirming things. Ruling out a 10 billion light-year structure that was never there would be its own contribution, a cautionary lesson in how systematically biased data can masquerade as discovery even under careful analysis. That lesson would be worth having. The timeline for THESEUS has shifted over the years, as proposed missions tend to do. ESA has considered it in multiple mission selection cycles, and its advocates have continued making the scientific case with each iteration. The technical capability is not speculative. The infrared spectrometer that would measure burst redshifts, the wide-field X-ray monitor that would detect the bursts in the first place, the architecture that would allow rapid follow-up within the same spacecraft rather than depending on a relay to ground-based observatories. None of this is beyond current engineering. The challenge is priority and funding, not physics. Other missions compete for the same resources. The argument for THESEUS has to be made against the backdrop of everything else the field wants to build. What makes that argument compelling is that THESEUS is not a single-purpose instrument. Gamma-ray bursts are interesting for dozens of reasons beyond large-scale structure. They probe the early universe. They mark the deaths of massive stars. They test general relativity under extreme conditions. They illuminate the history of star formation across cosmic time. A mission that captures all of that, while also resolving one of the most consequential structural debates in modern cosmology, is a strong case. But the Hercules-Corona Borealis Great Wall gives it a particular urgency. There is a specific, answerable question sitting in the data. An instrument exists that could answer it. Until something like THESEUS flies and delivers the data the field is waiting for, whether the largest known star in the universe is genuinely real remains one of the most consequential open problems in modern cosmology. The Hercules-Corona Borealis Great Wall did not arrive in isolation. To understand what its existence actually means, you have to see it against the background of everything else that came before it. Because there is a pattern here, and the pattern is strange. Go back to 1989. A pair of astronomers named Margaret Geller and John Huttrer were mapping the positions of galaxies out to a relatively modest distance, roughly 600 million light-years. What they found inside that volume was a thin sheet of galaxies stretching across their maps like a wall. They called it the Great Wall. At the time, it was the largest known structure in the universe, measuring somewhere around 500 million light-years across. The field stopped and stared. Nothing in the standard picture of how galaxies cluster had predicted something that large. There was a debate. Papers were written. The structure survived scrutiny and was eventually absorbed into the cosmological literature without anyone fully explaining why it was allowed to be that big. The models were adjusted sly. Work continued. What made this discovery particularly troubling was not just the scale, but what it implied about the universe's organization. The cosmological principle, a foundational assumption in modern cosmology, holds that matter should be distributed roughly uniformly across the larger scales. A structure of this magnitude suggested the universe had more inherent organization than the models accounted for. The tension remained unresolved, a theoretical puzzle filed away as observations continued. Then came 2003. A new survey, the Sloan Digital Sky Survey, was producing the most detailed three-dimensional map of galaxies that had ever been assembled. Inside that map, a team led by J. Richard Gott found another wall, longer than the first, stretching roughly 1.37 billion light-years. The Sloan Great Wall. It was nearly 3 times the size of what Geller and Hutra had found, and it immediately claimed the record. Same story. The field stopped. There was a debate. Some researchers argued the Sloan Great Wall was not a single coherent structure, but a chance alignment of separate clusters along the line of sight. Others disagreed. The structure survived partial scrutiny, the record was updated, and the theoretical tension it created quietly accumulated without resolution. The huge large quasar group arrived next. Quasars are the extremely luminous cores of active galaxies, powered by supermassive black holes consuming material at enormous rates. They shine so brightly that they can be seen across billions of light-years, which makes them useful for mapping large-scale structure in the distant universe, in the same way that gamma-ray bursts would later be used. In 2013, a team led by Roger Clowes identified a clustering of 73 quasars spanning roughly 4 billion light-years. This was the huge LQG, and it pushed against the cosmological principle just as hard as the structures before it had. The debate it triggered was still running when the Hercules-Corona Borealis Great Wall was published later that same year. It is worth pausing on the Clowes-Campusano Large Quasar Group, which came even earlier. Clowes and his colleague Luis Campusano found a grouping of quasars in the early 1990s that itself seemed too large when first reported. That structure was roughly 2 billion light-years across, smaller than the huge LQG, but it carried the same pattern. Too big, unexpected, debated, partially absorbed, unresolved. The Clowes-Campusano group barely registers as remarkable now, because every structure that followed it was larger. 2 years after the Hercules-Corona Borealis Great Wall was announced, a team at the University of Hawaii found something else using similar gamma-ray burst mapping methods. They called it the Giant GRB Ring. It measured roughly 5.6 billion light-years across, making it one of the largest known structures by angular extent, and it appeared as a ring-shaped overdensity of gamma-ray bursts in a particular region of sky. The Giant GRB Ring was debated immediately. Was it a genuine physical structure or a statistical quirk in the data? Sound familiar? The methods that found it were related to the methods that found the Hercules-Corona Borealis Great Wall. So the same methodological questions applied. The same unresolved tensions settled in. Then in 2021 came the giant arc. A PhD student named Alexia Lopez, working through quasar spectra from the Sloan Digital Sky Survey, identified an enormous arc-shaped concentration of material stretching about 3.3 billion light-years, sitting roughly 9.2 billion light-years away. Lopez was not looking for a megastructure. She was examining a particular spectral feature, the magnesium absorption signature found in quasar light as it passes through intervening material, and the signal of something enormous showed up in the data. The giant arc is not a gamma-ray burst result. It uses an entirely different tracer, different data, different methods, and it found the same category of thing, a structure far larger than standard models comfortably allow, located in a universe that was not supposed to be producing objects of that scale. The consistency was striking. Multiple independent discovery methods, spanning decades and using entirely different types of astronomical data, were all pointing toward the same troubling conclusion about cosmic structure. What connects all of these discoveries is not the structures themselves, but the reaction they each produced. Every decade, at least once, something has appeared in a survey that stopped the field cold. The structure was too big. The debate started. Researchers attacked the methods. Other researchers defended them. The signal proved stubborn. No clean theoretical explanation arrived. The record was updated. The tension was filed away. And then the next survey ran, and the next structure arrived, bigger than the last one. The Hercules-Corona Borealis Great Wall is the most extreme entry in this sequence. It is not slightly larger than the structures that preceded it. It dwarfs most of them by factors of 2 or 3 or more. But it is recognizably part of the same family, following the same pattern of discovery, debate, partial survival, and unresolved theoretical weight. The universe appears to manufacture large, coherent structures more readily than the models prefer, and it has been doing this consistently across decades of observations and improvements in survey technology. The signal has not gone away as the data have gotten better. If anything, the signal has gotten stronger. Each of those structures arrived as a surprise, and each one nudged the field a little further toward asking whether the models were capturing something true or missing something large. Step back from the data for a moment and look at what this argument is actually about. On one side, you have the cosmological principle, not just a working assumption, not just a convenience, a foundational claim about the nature of reality itself. The universe, at large enough scales, is the same everywhere and in all directions. This is the bedrock on which modern cosmology is built. The Lambda-CDM model, which is the standard framework for describing how the universe evolved from a hot, dense state to the web of galaxies we see today, inherits everything from this principle. Predictions about the cosmic microwave background, the expansion rate of the universe, the distribution of dark matter, the behavior of dark energy, all of it traces back at some level to the assumption that space is homogeneous and isotropic above a certain scale. That model has been tested against observation after observation for decades, and it keeps working. That is not nothing. That is a strong argument for taking the principle seriously. On the other side, you have the data. A region of the sky at redshift Z is approximately equal to 2 where gamma-ray bursts cluster so densely that the structure implied by that clustering spans roughly 10 billion light-years. Multiple independent analyses looking at the same region with different methods and finding the same signal. Subsequent reanalysis not shrinking the structure but expanding it, a feature that does not dissolve under scrutiny the way statistical artifacts typically do. The universe apparently built something. Whether that something is as large as the data suggest is still being argued, but the arguing has been going on for over a decade now. The signal has not gone away. The stakes of that conflict are genuinely large. If the cosmological principle fails at the scale of the Hercules-Corona Borealis Great Wall, it does not fail quietly. Everything downstream of it becomes suspect. The way cosmologists interpret the faint ripples in the cosmic microwave background depends on the assumption that those ripples represent a statistically uniform field across the whole sky. If the universe has large-scale inhomogeneities at the scale of 10 billion light-years, then different patches of the CMB might be telling different stories. Averaging them together would produce a number that does not accurately describe any particular region. The calculated age of the universe, 13.8 billion years, comes from models built on homogeneity. Dark energy, the term cosmologists use for whatever is driving the accelerating expansion of the universe, is quantified using observations spread across different directions and depths on the assumption that the underlying distribution of matter is roughly uniform. All of this interconnects. Pull one thread and the fabric shifts. That is a lot to put at risk on GRB clustering data alone. The critics who raised methodological concerns were not being obstructionist. They were being careful. Careful is exactly what you want scientists to be when the stakes are this high. A 5 to 20% probability that the signal is noise is not a ringing endorsement of a discovery that would require rewriting the foundations of cosmology. The field was right to demand more before drawing sweeping conclusions. But the other side of that cuts just as hard. Science does not get to selectively ignore observations because they are inconvenient. The history of cosmology is full of moments where the data arrived before the theory was ready. The honest response was not to dismiss the data but to go find out what was generating it. When the universe's expansion was found to be accelerating in the late 1990s, nobody demanded that the result be ignored because it contradicted a cleaner picture. They labeled the unknown driving force and kept working. The Hercules-Corona Borealis Great Wall presents a version of that same challenge. If the clustering is real, the question is not whether to accept it, but what to do with it. What would it take for the models to accommodate a structure this large? The short answer is that nobody has a fully worked out version yet. Some researchers have explored whether inflation models with non-standard parameters could produce density fluctuations large enough on these scales to seed such a structure. The numbers are difficult. Others have raised the possibility that the structure is not a single coherent object but a complex of related overdensities. That what looks like one enormous thing from our particular vantage point is actually several large things roughly aligned. That would make it slightly less catastrophic for the models, though structures of several billion light-years each would themselves require explanation. The possibility that we are seeing a genuine alignment of separate structures rather than one continuous object has not been ruled out, but it has also not been demonstrated convincingly. The honest position, the one most researchers working in this field will give you if you push them, is that the data are real, the signal is persistent, the theoretical framework for explaining it is incomplete. The instrument that would settle the question has not been built yet. That is not a satisfying place to land. It is, however, an accurate one. What the Hercules-Corona Borealis Great Wall has already done, regardless of how the debate resolves, is change the terms of the conversation. Before 2013, the cosmological principle sat largely unchallenged as a working assumption. The structures that had been found up to that point, the Sloan Great Wall, the large quasar groups were large enough to raise eyebrows, but not large enough to constitute a crisis. The Hercules-Corona Borealis Great Wall moved the needle. It forced cosmologists to take seriously the possibility that the universe's large-scale structure has not converged to uniformity at the scales we assumed it had. It prompted new analyses of the existing data, new proposals for future instruments, new theoretical work exploring what the models would look like if homogeneity holds only at larger scales than currently assumed. All of that is productive, regardless of the final answer. Whether the answer turns out to require new physics or simply a deeper understanding of what we already have. The Hercules-Corona Borealis Great Wall has made the universe a stranger and more unsettling place than it was before anyone noticed that clustering in the data